we're going to start off with the sum to product and product to sum formulas. These are the least important ones in the chapters. You don't have to memorize these, but you want to have seen them before because occasionally they're used. You don't want to say, what is that? Right? And so here's where they come from. Here's the first one. If I take this difference formula for cosine, cosine alpha minus beta is cosine alpha cosine beta plus sine sine. And cosine alpha plus beta is cosine cosine minus sine sine. And suppose I add those down, then the sines cancel over here and I get two of these. 2 cosine alpha cosine beta is equal to the sum of these. I divide this by 2 and switch sides, and I've got cosine alpha cosine beta is 1/2 cosine alpha minus beta plus cosine alpha plus beta. Now similarly, I can subtract them, and if I subtract them, this one minus this one, and divide by 2, then these two add, and I get 2 of these is equal to this one minus this one, and dividing by 2, I wind up, we'll just say similarly here, by subtracting and dividing by 2. We get that sine alpha sine beta is 1/2 cosine alpha minus beta minus sine cosine alpha plus beta. This is another product to sum formula. So you got 1, 2, and then there's one more. Let me bring up the book's rendition of it. That's enough proofs for the moment. So these are the 2 we did. Similarly, sine alpha cosine beta is 1/2 sine alpha plus beta plus sine alpha minus beta using the sum and difference formulas for sine, and then this one is essentially the same thing. You just reverse the sine and cosine. But we have 3 or 4 of these depending on how you think of them. Product to sum identities. Well, if you can turn a product into a sum, you'd think you must be able to turn a sum into a product, right? Well, if you try that also, you get these formulas. If you multiply those things through by 2 and I should do that. Let's just do one of these. In one, let's put theta equals alpha minus beta. Let's say gamma equals alpha plus beta. Now what we've got over here, putting these in, well, let's see, if I add these and divide by 2, I find out that theta plus gamma over 2 is alpha. And then if I take gamma minus theta and divide by 2, I get beta. And now I put those into equation 1, and I get, well, alpha minus beta is theta. I get cosine theta plus cosine alpha plus beta, well, that's cosine gamma. And that's equal to twice cosine alpha is cosine 1/2 theta plus gamma. cosine beta is cosine theta gamma minus theta over 2. And now you divide that through by, or multiply that through by 2. Let's see, no, I'm sorry, just leave it like that. Following from here, not directly from equation 1, the following, let's call it star. We've now derived a double angle identity that cosine theta plus cosine gamma is twice the cosine of their sum over 2 cosine of their difference over 2. Alright, so there's number 3. That's one of the sum to product identities. You can take a sum of trig functions and rewrite them as a product. So let's look down at those now. And here's the sum to product formulas. Cosine plus cosine is 2 cosine cosine, and so forth. So memorize that these exist, but you don't have to know the exact formulas. What I want you to be able to do is when I give you a problem, and I give you the formula, be able to rewrite a sum as a product or a product as a sum. Let's keep those formulas up here for the moment. Let's see. Let's try and use those to solve this problem here. Rewrite this product as a sum or difference. 16 sine 16x sine 11x. Well, where have I seen that before? I've seen it in this formula here. Let's see the previous one. And sine. If I treat this as alpha, and I treat this as beta, and I keep the 16 out front, I got 16 times, and I replace sine times sine with 1/2 cosine minus cosine. So 16 times 1/2 cosine of the difference, alpha minus beta, minus the cosine of the sum, alpha plus beta. Alpha minus beta is 16x minus 11x, is 5x. Alpha plus beta is their sum, 27x. So I can rewrite this as 8 cosine 5x cosine 27x. Now, if you can rewrite a product as a sum, we also said you can write a sum as a product. So suppose I try and rewrite this one. Suppose I have cosine 6t plus cosine 4t. Well, that came out to be twice. Let's put the formula back up here. Alright. Cosine plus cosine is twice cosine of the sum, cosine of the difference, we recall. So we've got cosine 16, we call this alpha and beta again. Cosine of the sum over 2, cosine of the difference over 2 is twice cosine of 5t times the cosine of t. One minor application to this is you can sometimes evaluate products that you couldn't before. Suppose I want to evaluate exactly the cosine of 45 degrees times the cosine of 15 degrees. Cosine 45 degrees, cosine 15 degrees. If you treat this as alpha and this is beta, by the formula we had gives us 1/2 cosine alpha minus beta plus alpha plus beta. This is 1/2 cosine 30 plus cosine 60. This is 1/2 square root of 3 over 2 plus 1/2 is square root of 3 plus 1 all over 4. That's the end of the sum to product and product to sum identities. This is all that's in the homework set. Please try and do all of those. But the idea is for the test, I'll just give you the formula and I'll say convert this product to a sum of the sum to a product. You just have to remember those formulas are there, how to use them. Well, the next topic then is solving trigonometric equations. This will be more difficult, a very long section. We're not going to be able to finish this tonight. The other one's too short to do the whole night on. This one's too long. So here's what we have. All sorts of trigonometric equations, and there's some real basic rules for these. They build on each other. So it's very important actually to do tonight's problems, be able to do the next nights. The easiest thing is to solve, so let's say solving trigonometric equations is the problem. And the first method is to solve trig function equals a number. Trig function of theta equals a number. To solve this, you just put it on the unit circle. For instance, suppose I had this one. Sine of x equals minus 1 over square root of 2. How do I find that? Actually, let's call it sine theta. Just make this a little easier on this one. rotation, sine theta. How do I find all theta between 0 and 2 pi? So within one rotation, include 0. Well, what you do is you say sine of theta is the y-coordinate on the unit circle, and it's supposed to be minus 1 over square root 2, so I draw all points in the plane that have y-coordinate minus 1 over square root 2. Then the two of them that are actually on the unit circle correspond to angles that theta could be. Right? If theta is this angle, or it has this terminal ray, or if theta has this terminal ray, then the sine of that angle will be minus 1 over square root 2 and otherwise not. So you want a point on the unit circle that has y-coordinate minus 1 over square root 2. Well, if we're restricting theta between 0 and 2 pi, we can't go this way. We can just go around to here or to here. So there's only two angles. And now, how do we solve those? Well, you drop a perpendicular to the x-axis. If I drop this perpendicular here, I notice because I went from 0 to minus 1 over square root 2, the length of this side is plus 1 over square root 2. This side is always 1 because it's the unit circle. That forces this last side also to be 1 over square root 2. It's a 45, 45, 90 triangle. So here it is. If I put 0 to 2 pi, that means I want you to use radians. If I say 0 to 360, that means I want you to use degrees. So this one I'll put in radians and say this must be pi over 4 because it has a square root 2 over 2, 1 over square root 2, 1 over square root 2, 1 triangle. Now that being the case, the angle here that goes around to this position must be pi plus pi over 4 is 5 pi over 4. So there's one solution. Now the other one, this one I go all the way around and back up this far, and what is that? Well, I drop the perpendicular here. And again I get side 1 over square root 2 because I went down to minus 1 over square root 2. This is 1, and the Pythagorean theorem forces this last side to be also 1 over square root 2. It's a 45, 45, 90 triangle. This angle right here must be 45 degrees, pi over 4. It follows that this big angle here is 2 pi back up pi over 4. Well, 2 pi is 8 pi over 4. I subtract 1 pi over 4. I found out this angle is 7 pi over 4. Evidently there are two answers, 5 pi over 4 and 7 pi over 4. Now what you want to be able to do is not just solve it for theta within one rotation. What if I want to solve it for all angles theta, no matter how positive or negative they are? What can I do? Well, you look at your picture and you say, the only way I can get sine, the y-coordinate, to be minus 1 over square root 2 is to have one of these two terminal rays. The only thing I'm missing is adding whole rotations to this. So I could go 2 pi plus this angle, or 4 pi plus the angle, or minus 2 pi plus the angle. So now the next angle, the next problem is to solve sine theta equals minus 1 over square root 2 with theta arbitrary. What do I do for that? I just take my answers I had last time, 5 pi over 4 and 7 pi over 4, and I can say I can go any whole number of rotations, so I'll add 2k pi to each of these. Why do I add that? Because one rotation is 2 pi, k rotations is k times 2 pi. By convention, we always just multiply in the other order and call it 2k pi. So k times 2 pi, or 2k pi, is k whole rotations around the unit circle. These are all the angles, no matter how big or small, that have sine equal minus 1 over square root 2. Well, we we want to be able to do this with all trig functions. Solve trig function equals a number. This is the simplest problem. Make sure you get this one down, and then we're going to build on it next time. Suppose I did this example. Suppose I want to solve cosine theta equals minus 1. How about that one? Well, cosine theta is the x-coordinate of the unit circle. The way you do these is, we said, you draw the unit circle. I want the x-coordinate to be minus 1. Here's the line, x equals minus 1 of all points in the plane whose x-coordinate is minus 1. There's only one of these on the unit circle. It's right there. It follows that there's only one terminal ray that can get you that x-coordinate. That's theta equals pi. And if I want to solve for theta between 0 and 2 pi, there's only one solution, theta equals pi. But if I didn't say restrict it to be between 0 and 2 pi, then I have to add any k whole rotations, and we'll say, so it's pi plus 2k pi. It's just any odd multiple of pi. So there's the answer to that one. Well, that's all right for sine and cosine. And what about the other trig functions? Well, for instance, this one. Suppose I wanted to solve tangent theta equals minus the square root of 3. And this time, let's restrict again theta between 0 and 2 pi. That'll save us the 2k pi in the end of the answer. What are all solutions to that? This one's a little trickier. There's a number of ways to do this, actually. One way to do it is just to remember this looks like y over x. So if I want square root 3 equal, minus square root 3 equal y over x, what I could do is rewrite minus square root 3 as minus square root 3 over 1. And then if I divide by the root sum square of these, if I calculate the square root of minus square root 3 squared plus 1 squared, well, that's square root 4, it's 2. I can now divide the top and bottom by that, and say this is the same as minus square root 3 over 2 over a half, or I could put the minus at the bottom, and I could call this square root 3 over 2 over minus a half. And I'm going to say that this can't be a point on the unit circle, y and x, because it's too big. Square root 3 is already 1.732, right? Approximately. So what I've done is when I divide through by the root sum square, this becomes a point on the unit circle. If you divide by the root sum square, then this squared plus this squared is 1 makes it on the unit circle. Same thing with this one. So there's 2 points on the unit circle that have tangent equal minus square root 3. And I'll give you a hint, whenever you have tangent equal a number or cotangent, then the angles are always directly opposite each other. You'll find that out as you do a lot of problems. But on the unit circle, I now go to this point, y equals square root 3 over 2, x equals minus a half, and take that point right here in this angle, or the one straight across. Y equals minus square root 3 over 2, x equals plus a half, is this point down here, and they're directly opposite. How do I find the angles that work there between 0 and 2 pi? Well, I have to go this way. I can't go counterclockwise. That will give me clockwise. That will give me a negative angle. So I figure, let's see, square root 3 over 2. If I drop a perpendicular again, that's the y coordinate, square root 3 over 2. And this is 1, so this has to be a half. It has to be a 30, 60, 90 triangle. So this would be 60 degrees pi over 3. In order that these add up to pi, this one has to be pi. Take away that pi over 3, it has to be 2 pi over 3. So that's one solution. And then the other solution is always 180 degrees around. So the other answer, this one, would be 2 pi over 3, the angle I got, plus pi. Evidently, I have two solutions. Theta is 2 pi over 3 to get here, or 3 pi over 3 plus 2 pi over 3 is 5 pi over 3. Two solutions for this one. That's it. If you got sine equals a number, you just try and find, you draw the line y equals the number and see what points on the unit circle you can get. If you have cosine equal a number, you put that for x. Tangent, you put it as y over x, try and divide by the root sum square to get a point on the unit circle. How about this one though? Suppose I had one of the other three trig functions like cosecant. Theta equals minus 2 over the square root of 3. How are we going to solve that one? Rewrite it as sine. So the other three trig functions, you take their reciprocals. This says that 1 over sine is this number. Consequently, taking the reciprocal of each side, I have sine on the left equals minus square root of 3 over 2 on the right. So I go to the unit circle, and if I want the y coordinate to be minus square root of 3 over 2, way down here, there's that line of all points that was y coordinate minus square root of 3 over 2. I notice there's 2 points on the unit circle. So there's 2 terminal rays. And if this is square root of 3 over 2 here, then this must be square root of 3 over 2 down. This must be a half over this one across. And this then has to be a pi over 3 angle. That being the case, let's say suppose we're solving this again for theta between 0 and 2 pi. Then I can't use this angle, I have to go all the way around. Here we go. If this is pi over 3, then by symmetry, this also has to be pi over 3. So we get one, the other one's isometric. That makes this angle pi plus pi over 3. Must be 4 pi over 3. This last angle here is 2 pi back up pi over 3, right? That makes it 5 pi over 3. This is 6 pi over 3 minus pi over 3. There are 2 answers only between 0 and 2 pi. Theta equals 4 pi over 3 or 5 pi over 3. If you want all angles, you just add 2k pi to each, where k, whenever I write it, means any integer, a number with nothing after the decimal point. You're allowed negatives, it's just not fractions. Well, that's it for trig function equals a number, so we step it up one. Let's just do a little more tonight and say, next, step 2, we can solve a linear equation. A times trig function. Okay, so the camera ran out again. We were talking about solving what's called a linear equation in a trig function. A number a times a trig function plus a number b equals 0. We can solve that by simply subtracting b and dividing by a, so you get trig function equals minus b over a. Then you just go to method 1. So these methods are all going to build. Here's a simple example. It illustrates better just by doing one than by saying it sometimes. Suppose I had 2 cosine theta minus 1 equals 0. How can I solve that one, right? Well, I add 1 and divide by 2 and just write it equivalently as cosine theta equals a half. And then I use method 1 because this trig function equal a number. Now, method 1 says this. I draw the unit circle. Cosine is the x-coordinate, so I want the x-coordinate equal a half. Here's a half about halfway across here to 1, right? these are all points in the plane with x-coordinate equal 1. There's only 2 of them on the unit circle, 2 points on the unit circle, which means there's only 2 possible terminal rays. This one or this one. Alright? Now we know that x is a half, so this side length right here is a half, and if I drop my perpendiculars, this angle here is on a triangle, it's 1/2 and 1. By the Pythagorean theorem, this one would have to be square root 3 over 2. This must be, let's do it in degrees this time and say we'll solve it for 0 less than or equal to theta less than 360 degrees. So this must be a 60-degree angle. By symmetry, right, this triangle is 1/2 also in 1. That has to be square root 3 over 2. This also has to be 60 degrees. The other angle is not going this way, that'd be a negative angle, right? But instead we go around 360 back up 60. So here's this angle, 360, take away 60 is 300. And there's 2 answers. Theta is 60 degrees or 300 degrees. So there's the kind of problem we can solve also. And we should do the hard case again, huh? Hard case is tangent and cotangent. Suppose I have this example. Cotangent of theta plus square root 3 equals 0. Well, you just convert it into trig function equals the number by subtracting square root 3 and dividing by 1. This does nothing. So you get cotangent theta equal minus square root 3. Cotangent theta is x over y, so I need x over y in the unit circle to have this ratio, but if I just put this over 1, that won't be x and y. That point is outside the unit circle, so I divide by the root sum square of those. 2, rewrite this as minus square root 3 over 2. You can probably guess this division. Over a half, or you can also make it square root 3 over 2, or negative a half. And so this will be a point on the unit circle that has this cotangent, and this will be, and that's all. Let's solve this for theta between 0 and 2 pi this time. Now I go to method 1 because I have trig function equal a number. That's what I started here. And I say, well, x could be minus square root 3 over 2. Y could be a half. And at this point, the other one for tangent and cotangent is always directly opposite, so it'll be steered over here. But you can see it. Now I've got minus a half for y and plus square root 3 over 2 for x. Now I drop the perpendicular. If this is square root 3 over 2 and this is a half, this must be a pi over 6 angle, right? This one being pi back up pi over 6, straight angle minus pi over 6, must be 5 pi over 6. There's one possibility. And then, by symmetry, this has to be the same pi over 6. So I can go 2 pi back up pi over 6 for the other angle, this one. Is 11 pi over 6. So I've got 2 solutions. Theta equals 5 pi over 6 or 11 pi over 6. Alright, finally, let's try a problem where it's not a trig function of theta, but a double angle or a triple angle. So step method 3 is either of the above. If you have a times trig function of k times theta, a multiple of theta, plus b equals 0. What do you do for this one? You try and make it like the last one. So you just let u equal k theta. Solve on the unit circle for u. time, you don't restrict it to be between 0 and 2 pi, if this one is, solve for all u not between 0 and 2 pi, because when u is between 0 and 2 pi, theta goes between something else, right? So it won't give you the right range of angles if you restrict u between 0 and 2 pi. So not u between 0 and 2 pi, but all u. And then, after you have all u, put back, and this is on the unit circle. Then put back theta equals u over k. You get the theta values. So it's method 2 here. So if you get a trig, a times the trig function of k theta plus b equals 0, just make a substitution to make it a times trig function of u plus b equals 0. Then apply method 2 and then substitute back. Alright, so let's try an example. Suppose I wanted to solve 2 sine 2 theta minus square root 3 equals 0. How am I going to solve that one? Well, since it's not a trig function of theta, but of 2 theta, I'm going to let u equal 2 theta and rewrite this equivalently as 2 sine u minus square root 3 equals 0. Now I can apply method 2, right? On method 2, I'm now going to add square root 3 and divide by 2 and get equivalently sine u equals square root 3 over 2. Now suppose on this one I wanted to restrict theta between 0 and 2 pi. Since u is 2 theta, that's going to restrict u to be between 0 and 4 pi, so I could do that, but I think it's easier to do what we just said. Just solve for all u, and then when, at the bitter end, go back and find which values of u correspond to theta being between 0 and 2 pi. So I'm going to solve this in the unit circle for all u. Sine is the y coordinate, so I draw the line y equals square root 3 over 2. Observe that there's 2 points on the unit circle, here and here. Drop the perpendiculars again. That makes this square root 3 over 2 because I went from y equals 0 to square root 3 over 2. This is 1. This must be a half, and this must be a pi over 3 angle. All these you get symmetry. This must be a pi over 3 angle, which means the 2 angles here are pi over 3 and pi back up pi over 3 is 5 pi over 3. Now, I can add any multiple of 2 pi to each other, right? K whole rotations is 2k pi. And there are all solutions u. But I want to restrict theta between 0 and 2 pi. So I put u is equal to 2 theta and divide by 2, and I get equivalently theta equals pi over 3 divided by 2 is pi over 6, 2k pi divided by 2 is k pi. Theta equals, dividing this one by 2, 5 pi over 6 plus k pi. That's all solutions theta. But we want to now restrict theta between 0 and 2 pi right at the bitter end. So you try small values of theta. Theta equals 0, 1, 2, minus 1. Those kind of things close to 0 until you get bigger than 2 pi or smaller than 0, and then you say, oh, those are out. So I'll try k equals 0 in the first equation, I get theta equals pi over 6 plus 0. That's between 0 and 2 pi. Then I put k equals 1. Pi over 6 plus pi is 7 pi over 6 if you do some quick adding. That's between 0 and 2 pi. But if you add 2 pi plus pi over 6, that's bigger than 2 pi. You throw that one out. So k equals 0 and 1 works here. Negative 1 makes this less than 0. That's too small. 2 makes it too big. So you just try around 0 and 1 until you get 1 too big and 1 too small. Similarly here, you try k equals 0. And you get 5 pi over 6 plus nothing. 5 pi over 6 is the solution. It's between 0 and 2 pi. If you put k equals 1, then you get pi plus 5 pi over 6 is 11 pi over 6. That's between 0 and 2 pi. But if I put k equals 2, it's 2 pi plus something. That's too big. Put k equals minus 1. That makes this less than 0. That's too small. There are 4 solutions to this one because of this double angle in the original problem. So those are a little tricky. Try some of these in the first part of the section, and make sure you can do all the sum of the product and product of sum formulas when you're looking at the formula and have the problem. That's all you need to be able to do. Then try these first few here. And I think beginning with problem 3, they have the next step, which is a times trig function squared plus b times trig function plus c equals 0. We'll do those next time, so I'm going to stop in the middle of the section.